Hello, and welcome back to Zero G Stargazing. If you didn't see the first video on the solar system and want to learn more about the planets, go and check that out. Today's video is going to be all about neutron stars, from their humble beginnings and explosive demise. Zip up your spacesuit and strap on in as we explore some of the most fascinating objects in the universe, right now. What exactly is a neutron star? Well, to put it simply, it's the leftover core of a dead star, usually created after a supernova explosion. But let's go back a step further and talk about what a supernova explosion really is. The first recorded supernova explosion, or you could also call them pop stars. Oh, you thought those jokes were in the first video? Yeah, no, they're gonna keep happening. Anyway, this event took place in the year 185, and it was observed by Chinese astronomers. They noted that it shone as bright as the full moon in the daytime sky for months before finally fading. A now famous supernova remnant was seen again by Chinese astronomers in the year 1054. This nebula is now known as the Crab Nebula, and we can see, surprisingly, it doesn't look anything like a crab. What we're looking at here is the exposed guts of a star that met its demise after losing a battle with gravity. Different colors seen are the chemical footprints of the cloud of gas and dust. During a supernova explosion, and much like someone who's eaten too much gas station sushi, mass can be ejected out at significant fractions the speed of light, allowing astronomers to even see the expansion in real time, albeit months at a time, but still, space is huge. The energy released during a supernova explosion is dwarfed only by the Big Bang itself. At a singular time, the supernova outshines an entire galaxy, producing more energy in 1 second than the sun will create in its entire lifetime. To put that into perspective, the amount of energy the sun creates in just 1 second is equivalent to the entire nuclear arsenal of Earth 150 million times over. Now, multiply that by 8 or so billion years, and that is the power of a supernova. Only in these hellish conditions do we see elements 6 through 37 be formed. But if you've seen a periodic table, you'll notice it doesn't stop at the element 37. So what exactly does it take to make all the other elements? Well, the answer lies in the leftovers of a cosmic war between stars and gravity. A star war, if you will. In most of the galaxy, stars have at least one or two others orbiting each other. Our sun is odd in this respect. In some of these pairs, astronomers will find that the smaller star will begin to absorb the larger one. After a while, the star will become more and more unstable, and unable to support the extra mass, leading ultimately to a complete destruction of the smaller star, and the other cannibalized star will finally be released and shot through interstellar space. When a large star explodes, one might expect that the only leftover is a nebula. Well, in most cases, that's not true. After a massive star's core starts to fuse iron, the star will begin to lose energy from the reaction instead of gaining it. Without the core of the star, it collapses in on itself, smashing electrons and protons together with enough force to create a core of pure neutrons. This energy then throws the outer layers of the star into space. This remnant is so dense that the core is now roughly the size of Manhattan, with a mass of 500,000 Earths. This is a neutron star, the most dense object an astronomer can observe in the universe. 1 teaspoon of neutron star matter would weigh more than an entire mountain. However, most neutron stars are believed to be undetectable because they don't emit a lot of radiation because of their size. But the ones we can detect are either the centers of supernova remnants like the Crab Nebula or the Spaghetti Nebula, which we can see at least astronomers were smart enough to name this one after something without a definite shape. Now is when the rest of the periodic table comes into play. Occasionally, 2 of these Manhattan-sized orbs of hot neutrons will happen to be orbiting each other. This cosmic dance doesn't last too long. They begin to spiral into each other, closer and closer until they smash into each other, completely destroying the two, being one of only 2 events in the known universe to create detectable gravitational waves. But wait, this large ball of neutrons gets even cooler. I know it's a star, but it does get pretty cool. Many neutron stars belong to a different class of stars, called either a pulsar or a magnetar. These names come from the properties of the star, although at the end of the day, they are still neutron stars. First, the pulsar's defining characteristic is its rapid spin. In fact, the most commonly found type of neutron star is a pulsar. They have incredibly strong magnetic fields, which take material from surrounding space, heat it up, and trap it in the poles of the magnetic fields. In most cases, the star's magnetic field is different from the axis it spins on, causing the hot charged particles to sweep around the star as it spins. Here on Earth, pulsars were once thought to be messages from intelligent life. In 1967, a very regular radio source was picked up by astronomers who labeled the data LGM for Little Green Men. What they were actually hearing was a neutron star. These pulsars are so regular that they can be used as the most accurate clocks in the universe. And the fastest pulsar spins at over 700 times a second. Pulsars are defined by their spins from Earth, or their pulses that we hear. With magnetars, you can only guess what makes them so unique. I would like to thank astronomers that came up with the name pulsar and magnetar. These are actually very awesome names. Regardless of the names though, magnetars are some of the most fascinating objects in the universe. They really pull you in with their unique properties. From the North Pole to the South Pole, everyone can agree magnetars are really interesting objects. Okay, enough of the puns. Magnetars have an unimaginably strong magnetic field. Regular neutron stars have magnetic fields trillions, with a T, of times stronger than the Earth's, and magnetars have a magnetic field about 1,000 times stronger than that. These conditions are so powerful that the field itself can twist atoms themselves into spindles, or tubes. Getting farther in towards the star, the core, it may be so intense that the atoms themselves have broken into their individual parts. A core of quarks, the building blocks of the universe. Hid under a magnet so powerful that it would strip your credit cards from over 100,000 miles away. Magnetars can occasionally, through a process not entirely known yet, have its surface crack, a starquake, creating an insane amount of X-ray, radio, and gamma waves that we can detect here on Earth. There are only about 10 known magnetars in the galaxy. One has recently shown to be active in the Cassiopeia Nebula. These incredible objects offer us a look into the cutting edge of astronomy and physics, pushing the very limits of what we think is possible. One of the most famous examples of this is actually related to the hunt for planets outside of our solar system. The first exoplanet ever discovered was actually found orbiting a pulsar, and to this day is still making astronomers ask questions about how planets are formed. I hope you all like this exploration of some crazy stars. Tune in next time, and don't hesitate to leave a comment letting me know something else you'd like to hear about. And as always, stay curious and have fun learning.